Alright, so these are the notes on mole ratios and some examples that we're going to work through for calculating the moles of chemicals from a balanced reaction. So in class we've taken a look at our s'mores chemistry as an example for mole ratios and thinking of a reaction kind of like a recipe. So we did this one before, looking at a simple example. We had our graham crackers and marshmallows and chocolate pieces and used that to think to make one s'more. So we're looking at a ratio between our different pieces in this recipe. We can think of a chemical reaction the same way. So in this chemical reaction, that's our example here, we want to look first at the coefficients that are given. So we have nitrogen, N2, plus hydrogen, giving us NH3, which we call ammonia. And we can see the coefficients are 1, 3, and 2 in this reaction. So the 1 in front of the nitrogen tells us that for every 1 molecule of nitrogen, we need 3 molecules of hydrogen, and that will make 2 molecules of ammonia. But also, as we've discussed in class, we know that 1 molecule is not enough. 1 and 2 molecules are not enough to make a significant amount. So we are going to think of our coefficients as moles. Okay, they're going to represent our moles. So when we look at our balanced reaction, we have 1 mole of nitrogen reacting with 3 moles of hydrogen to make 2 moles of ammonia. And remember, a mole is just, it represents that 602 hexillion particles. So we're still keeping the same ratio, we're just thinking about it in much larger numbers. Remember though, a mole is like a counting unit, kind of simplifies things for us. So we don't have to use 602 hexillion in front of our chemicals here. We can use these simple whole numbers and think of it in terms of moles, since moles are a universal number or unit in chemistry. So it says use the reaction above to answer each of the following. So for every 1 mole of nitrogen, N2, blank moles of ammonia are formed. So we look at our reaction here. For every 1 nitrogen, we are going to make 2 moles of ammonia. Okay, so that is our ratio. We're just kind of thinking through some ratios here. To react 6 moles of hydrogen, so if we looked at this, we have 3 here, so 6 is twice as much. So we could think of this as multiplying it by 2. Blank moles of N2 are needed. So if we multiplied hydrogen by 2, we'd also have to multiply our coefficient of nitrogen by 2. So 1 times 2 gives us 2. So to react 6 moles of hydrogen, we would need 2 moles of nitrogen. We need twice as much on both of them. And our last one says to form 12 moles of ammonia, NH3, blank moles of hydrogen and blank moles of nitrogen are needed. So if we wanted to get to 12 moles of ammonia, we'd have to multiply this by 6. So we'd want to do that to all of them. So 2 times 6 would give us 12. 3 times 6 would give us 18 moles of hydrogen. And 1 times 6 will give us 6 moles of nitrogen. So it's like taking all the coefficients and multiplying them by a number to see what the relationship is, by a whole number. Now, not all of our problems will be that basic. We might have more complex problems to look at where we don't have whole numbers. So we're going to take a look at how we can set those up. So it says, these are easier to do because we're dealing with whole numbers. When we have numbers that are not easily multiplied or divided, we can set up an equation to help us solve it. It follows this setup. So the way we set it up is just like we did when we did conversions at the very beginning of the year. We're going to do it using our railroad tracks. So we always are going to put our given value in moles first. On the bottom, we're going to put the moles of the chemical that's given. On the top, we're going to put our moles of our chemical wanted. Both of these numbers, our values, are from the balanced reaction. Okay, we're going to get them from our coefficients. So let's take a look at an example. It says how many moles of NH3, so that's what we're looking for, will be formed if 7.35 moles of hydrogen react. So we're going to start with our given value in moles. So here's our given value, 7.35 moles, and its chemical is hydrogen. We're going to follow our pattern here. It says moles of chemical given. So our chemical that's given is hydrogen. So we're going to automatically bring this unit and this chemical down to the bottom. We want these two to be able to cancel out. And then on the top we want the chemical wanted. Moles of the chemical wanted. We want NH3, so we're going to put that on the top. Okay. So now we need to fill in its numbers. We always fill in our units first so we know where things go, and then we're going to fill in our numbers. And our numbers are going to come from this balanced reaction, the same one. So I'm going to rewrite it over here so we've got it handy. We've got N2 plus 3H2 forms 2NH3. So there's our coefficients. So we're going to look at this. We have moles of hydrogen on the bottom. So we're going to go to our balanced reaction, and we're going to see how many moles of hydrogen are represented there. And it's 3. I'm going to bring that 3 over. And then we're going to go to our balanced reaction. We want to find moles of ammonia. So here's our moles of ammonia. Its coefficient is 2. We put 2 moles of ammonia. So it's really just taking this balanced reaction and translating it into a fraction or conversion factor in our equation. Now at this point, we have our problem set up, and as we've seen before, I know it's been a while since we've done this, but we multiply on the top and we divide on the bottom. And then we can cancel our units. We always want to, the reason why we transfer these moles of hydrogen to the bottom is because we want them to cancel out. So those two will go away, and we just need to do our calculation. So in my calculator, I'm going to take 7.35. We're going to multiply by 2 on the top, divide by 3 on the bottom, and we get 4.9. The unit that's left over is moles of NH3, ammonia. Okay. So we can approach it this way when we don't have nice, clean numbers to deal with. It's a little harder to think of these coefficients in kind of weird ratios like these. So we're going to take a look at another example here. Alright, we have a new balanced reaction, so we can see our coefficients on each chemical. It says for every blank moles of Fe2O3, blank moles of CO2 are formed. So for every 1 mole of Fe2O3, blank moles of CO2, so 3 moles of CO2 are formed, and we're just getting that from our coefficients on those. So it's just making comparisons between two chemicals. Alright, this says if 9 moles of CO react, so 9 of these react, blank moles of iron Fe are formed. So if we went from 3 and we wanted to get to 9, we'd have to multiply that by 3. So if we also multiply 2 times 3, we'd get 6. So for 9 moles of CO, we need 6 moles of iron. Alright, and then the next question, how many moles of iron, so that's what we're looking for, will be formed if 3.62 moles of CO2 or from 3.62 moles of CO2. So we want to follow our same setup from above. We want to start with our given. We want to bring down our unit, moles of CO2. And then we want to write down what we're looking for, moles of iron. So we can do all of this part just from the question without looking at our balanced reaction at all. Now we want to look at our balanced reaction and get our ratio. So we can find our moles of CO2. We find CO2 in the reaction, which is here, and its coefficient is 3. And we find iron Fe, and its coefficient is 2. So for every 2 moles of iron, we have 3 moles of CO2. Again, our units will cancel, and we can do our calculation. So again, we want to multiply what's on the top and divide by what's on the bottom. So we have 3.62 times 2 divided by 3. 2.4. And when you get a long decimal like this, you can just round to like the second digit. The second decimal place is fine. So for us, 2.41. And then we want our units that are left over and that they were asking for, moles of iron. All right. Here's one more. So it says how many moles of CO, that's what we're looking for, will react to form 1,083 moles of CO2. So we can see these are different questions. In this one we're talking about moles of iron and moles of CO2. This one we're talking about CO and CO2. We can compare any two chemicals in our reaction to each other, which is what makes these moles so powerful. So again, we want to start with our given 1083 moles of CO2. This one I took away the setup, so you got to draw your own railroad tracks in. We want to bring down our unit, moles of CO2, and we want to fill in what it's asking for, moles of CO. And we want to look for those in our chemical reaction. Now be careful between your CO and your CO2. Make sure you're using the right one. So we've got 3 moles of CO and 3 moles of CO2. Well, that's convenient. Both numbers 3. Again, our units, moles of CO2 will cancel. And if we're multiplying by 3 and then dividing by 3, we could reduce those to 1 and 1, and our number will stay the same. And sometimes that happens. Whenever it has the same numbers for our coefficients, this might happen. But we still want to show our conversion and what we're changing to, what new chemical we're looking at. Okay? So at the bottom has our steps. This is the process we went through. We write down our given and set up our railroad tracks. We transfer the units from the chemical given to the bottom right corner. We write the units and our chemical wanted on the top. We fill in the mole ratio from the coefficients in the balanced reaction. Cross out the units that cancel. We multiply on the top and divide by any numbers on the bottom, and write our answer with its units and chemical. So it's pretty straightforward, and then you guys can try the practice on the next page in your notebooks.